Hello, welcome back. My name is Eric Wolf, and this is Chapter 2, Close Encounters of the Third Dimension. In the beginning, there were 1D models. And well, 1D models, they're still everywhere. Why? Because they're very useful and they're very fast. 1D models are used for things such as calculating latitudinal energy balance. Boudico in 1969 did one of the first calculations of the sea ice albedo feedback and on long timescale processes using such a model, or the venerable Jim Casting et al. Radiative convective model with 1D in the vertical, which includes radiation and convection and has elucidated such processes as runaway greenhouses and dense CO2 atmospheres and processes around different stars and things like that. So 1D models have and will continue to teach us many great things, such as the standard definition of the habitable zone from Casting et al. 1993 and later updated by Kaparapu et al. 2013 with a model now known as CLIMA. You might also know it from its pairing with the chemistry called Atmos, so Atmos CLIMA. So here we have the conceptual limits to the habitable zone that we all know so well nowadays, such as the runaway greenhouse, the moist greenhouse limit, or the maximum CO2 outer edge limit. This figure is from Kaparapu et al., showing these limits on the habitable zone across a wide variety of stars. 1D models are also extensively used with coupled chemistry, such as here from Meadows et al. 2018 with the VPL climate 1D model, showing what the atmospheric constituents may look like, photochemically driven, for Proxima b, with a pre-industrial Earth baseline composition or an modern Earth-like baseline composition. However, over the last decade or so, 3D climate models have begun to find their niche in exoplanet modeling. Here, I'll leave this up for a second. I show 4 different images of what 3D model output data looks like in rich detail with specific humidity at the top left, a cloud pattern at the top right, a cloud pattern from a different world with a different rotation rate in the bottom left, temperature fields at the surface in the bottom right. So 3D models give this full grasp, both in time, 3D space and time, of what these exoplanets may look like and how they may be habitable and where water may exist on the surface. And it also elucidates complex physical processes occurring on these planets. So what can GCMs tell us about habitable worlds? Well, they give us a more complete model of climate. If you remember from chapter 1, I discussed that climate models couple many different processes together in a 4-dimensional context, 3 dimensions of space and 1 of time, to help us answer, can liquid water theoretically exist on a planet's surface? So you take your GCM, which has been suitably modified to be able to handle inputs different from Earth, and you feed it your parameters, your stellar flux of the planet, your stellar energy distribution, your surface pressure, your greenhouse gas amounts, and then there's certain 3D specific elements such as the rotation rate of the planet, obliquity, things like that. There's also eccentricity of the orbit, land-ocean fractions, different continental configurations, the radius of the planet, the surface gravity, and then the model will compute and it will determine self-consistent climate with different feedbacks which can threaten habitability, such as entering into a runaway or moist greenhouse process through time, entering into a snowball climate, atmospheric collapse near the outer edge of the habitable zone, and ultimately you can determine if your given set of planet parameters and atmospheric choices and surface choices, for instance, can yield habitable states. So the secret sauce for 3D GCM is in its ability to treat complex coupled processes simultaneously and realistically in 3 dimensions and in a time marching nature. Collectively, the whole is greater than the sum of its parts. So in lower dimensional models, you can devote, they're much, much faster, and you can devote more computational time to doing better radiative transfer or better chemical calculations. But the GCM, its specialty is trying to incorporate the coupling of all of these processes, how radiation and dynamics and clouds and heat transport all collectively interact, which often can elucidate different climate feedbacks that we might not see in lower dimensional models. So what have we learned from GCMs about habitability so far? Well, lots of things, really. One big thing is we've learned refinements to the habitable zone for Earth-like planets, along with different nonlinear climate transitions, which affect the habitable zone limits. In this plot, we show from Wolf et al. 2017, the climate evolution of an Earth-like planet around a K dwarf, a G dwarf, and an F dwarf. You see that there's different climate states which are possible, different regions in space where no stable climates are possible, different sharp transitions into moist greenhouses, sharp transitions into a snowball, stabilization of water belt states. And many of these things only come about due to the 3D nature of the climate that has been modeled. So in particular, the inner edge of the habitable zone, 3D models have shown you can push it inwards compared to 1D by 10 to 20% in terms of stellar flux due to reduced relative humidities at low latitudes combined with cloudiness, both of these which are strongly modulated by the 3-dimensional circulation of the atmosphere. Likewise, towards the outer edge, when you get into thinking about snowball planets and water belt states, these are often critically dependent upon heat transports also from the ocean and the atmosphere, which can best be captured with a 3-dimensional model. Here, we show results from Turbay et al. 2017 with the LMD generic model, exploring the CO2 condensation limit at the outer edge of the habitable zone. So in the plots, time is the bottom axis in terms of solar longitude, and you see regions where CO2 ice clouds are condensing in the sky, and also regions where you have surface condensation of CO2 and surface sublimation of CO2. So at this maximum CO2 outer edge of the habitable zone, when you rely on lots of multiple bars of CO2 to keep a planet warm, if you treat the problem with a 3D climate model, you actually see there is a massive change in the outer edge of the habitable zone. Paparapu showed the outer edge around the sun is about 1.7 AU in with a 1D model. With a 3D model, CO2 actually begins to condense on the cold traps at the poles beyond about 1.27 AU. So again, this is a 3-dimensional effect that is only truly captured with a 3-dimensional model where you can model the cold traps of the planet instead of a single global mean profile. We've also learned that planets around M dwarfs are weird and cool. So we know that planets around M dwarfs are likely locked into synchronous rotation, meaning that one side of the planet always faces the star. And this leads to very weird circulation patterns and also cloud patterns. So here, simulated with the ExoCam model, on the left we have Earth, and on the right, we have a slow rotating Earth-like planet around an M dwarf. So the top images, the top movies are of specific humidity and on a vertical slice around the equator. And the bottom is the total grid box average cloud water path. And you can see for Earth, water vapor is trapped near the surface. And you see your familiar cloud maps of the Earth where you have mid-latitude storm tracks moving west to east and an equatorial motions from east to west. Well, it looks very different for the slow rotator. The slow rotating planet, you end up with a big day to night side circulation, which pumps a lot of water vapor high up into the atmosphere, as you can see in the top movie on the right. And then for slow rotators, you see they form this big cloud shield originally shown by Jun Yang and many others now, which greatly enhances the albedo of the planet. So these slow rotating M dwarf planets can actually remain habitable much closer at much higher stellar fluxes than Earth around the sun due to the high albedo from from the clouds, which is a three-dimensional general circulation effect. And we can see here that it's not a singular binary slow rotator versus Earth process. If we look at different rotation rates, slow rotate 85-day on the left, 8 days in the center, and TRAPPIST-like, well, it's 4.5 days on the right, you can see that the general circulation changes significantly between the three cases, driving very different cloud patterns for tidally locked planets around M dwarf stars. We've also learned from 3D models that a coupled dynamic ocean can have significant effects on surface climate. So these are simulations done with the Rocky 3D model for planet Kepler 1649c. So at the top is a slab ocean model, which I'm guilty of using too often due to its computational expediency. With a synchronous rotator, you get that nice eyeball climate where it's warm at the substellar point, cold on the backside. And a 3-2 resonant climate with eccentricity, you end up with this double eyeball pattern where each side of the planet periodically gets irradiated at a high level. But if you include dynamic ocean heat transport is quite significant for surface climate, as you can see forming this stingray pattern in the synchronous case, where the ocean can transport heat in a zonal band around the equator, nearly all the way around the night side. And then for the resonant case, you see a nearly zonal Earth-like pattern as heat is very efficiently transported. So dynamic ocean heat transport in 3D can lead to significant effects on surface climate. So we've also learned a lot about solar system applications for habitability. So the same mechanisms that affect slow rotating planets around M dwarf stars could also be applied to Venus. So it's been shown here with the Rocky 3D model again, that ancient Venus, if it had the same rotation rate as it does today, could actually have been habitable. Why? Well, the same mechanism that we see from M dwarfs. If there was originally water on the surface of Venus, its slow rotation would have promoted a big, thick substellar cloud deck. You can see on the left a plot of the shortwave cloud radiative forcing is strongly negative near the substellar point, which could have kept Venus habitable for the first few billion years of its history. This is a very interesting possibility and one of the motivations that we should go back to Venus and see if we could investigate whether this hypothesis is true. And then what about early Mars? Well, you can use a 1D model to study whether early Mars could have been kept warm despite the faint young sun based on different greenhouse loadings of CO2 or H2 or methane or what have you. But 3D models have posed a very interesting view and solution to early Martian climate, which you could not get from a 1D model. So here from Wordsworth et al. 2013, using the LMD generic model, it is shown on the left that water would preferentially be cold trapped on the Martian highlands, the high parts of the topography, and then short period warming events may have caused melting, periodic melting to cause the riverine features that we see today on Mars. So this is known as the icy highlands hypothesis, shown on the right, where the water ice gets cold trapped in the highlands. Perhaps an impactor or different release of greenhouse gases from volcanism may have caused periodic melting events to let the river features form on early Mars. So we don't necessarily need a binary picture of Mars. It's either warm or it's cold. We can have this intermediary picture, the icy highlands hypothesis, that's really only elucidated through the use of 3D models. 3D models also have numerous applications for thinking about the habitability of Earth through time, including the faint young sun paradox. How did the Earth stay warm despite a reduced solar constant? Or the dynamics of snowball episodes and other such problems. This is a plot made by Chris Kolos, also with the Rocky 3D model, showing the dynamics of a water belt state of the advancement of sea ice. This is a continuing field of study, thinking about the early history of Earth and snowball episodes that may have occurred. Also, we can think about very novel applications. This is one in particular I think is pretty darn cool. This is from Bardeen et al. 2017, using the NCAR Wacom Karma model, which asks the question, what is the climate ramifications of the asteroid impact that killed the dinosaurs? So you can use a 3D model to simulate such an event by injecting massive amounts of soot and aerosols into the atmosphere, simulate the aftermath of a meteor, an asteroid impact as such. And you can see on the left how you have a severe reduction in global temperature, reduction in precipitation that would have resulted in many of the plants dying. And on the right, you see atmospheric temperatures and ozone loss. So this is another novel problem related to habitability of Earth through time that could be elucidated through the use of a 3D model. So the take-home points here are that we've actually learned a lot about habitability from GCMs for a wide diversity of problems. So the Earth through time, including the faint young sun paradox, snowball episodes, the effects of meteor impacts, solar system objects through time, Venus perhaps being habitable during an earlier period, the icy highlands hypothesis for early Mars. We've learned a lot about exoplanet habitability, in particular refinements to the habitable zone of both inner and outer edges. Also, the climate and habitability of slow rotating M-dwarf planets. And all of these were elucidated by distinctly 3D coupled processes from GCMs. So we will continue to use GCMs to study many of these novel problems. So not just for habitable exoplanets, but for solar system objects as well.